Hello, this is question 9 from the Step 2 paper in 2022, and we've got some mechanics, which is a good thing. I do like a mechanics question, so it's good for me anyway. A lot of people don't like these, but we'll see how I get on with it all. A rectangular prism is fixed on a horizontal surface. A vertical wall parallel to a vertical face of the prism stands at a distance d from it. Right, let's start getting this into a picture. So a horizontal surface, it's fairly horizontal, and a rectangular prism. So I'll just draw that as a block, something like that. And then a vertical wall, I should say, parallel to a vertical face of the prism at a distance d. So vertical wall at distance d. Okay. Light plank making an acute angle theta with a horizontal rests on the upper edge of the prism. So it's resting here, makes contact with a wall below the level of that edge of the prism and above the level of the horizontal plane. So let's say there. So I've got a plank doing something like that at angle theta. Right, you may assume that the plank is long enough and prism high enough to make this possible. Okie dokie. Contact between the plank and the prism is smooth. The coefficient of friction at the contact between the plank and the wall is mu. So we've got a rough wall, smooth block, blocks fixed. When a heavy point mass is fixed to the plank at a distance x, right, so it's not going to roll along it, along the plank from its point of contact with a wall, system is in equilibrium. So I could put it, say, here. I suppose it's going to change things a bit when it goes past that contact point with a prism, because then we're going to get a sort of different, well, on the other side of a pivot point, so you get a different moment going on there. But still, I'll put it there for now and see how that goes. And the system's in equilibrium. Right, so let's put some force arrows on all of this. So we've got an mg for that mass. We've got a normal reaction here, and I'll call that R. There's no friction going on at that point. That's smooth. We've got friction at the wall. So we've got a normal reaction at the wall. So I'll call that one N, as I've already used R. And then in this setup, I mean, it looks to me as though that fixed mass is going to be pushing the end of the plank next to the wall downwards. So I'm going to draw the friction going upwards then. But that is going to change at some point, isn't it? If we move that fixed mass far enough along the other way, then the friction is going to flip in the other direction. Whether that happens as soon as it goes past the pivot point is another matter, but friction could be going in either direction. I think is what I'm getting at in this setup. So part 1, show that if x equals d sec cubed theta, there's no frictional force acting between the plank and the wall. Right, so that's our limiting case then, or our transition case, where the friction is flipping sign. So what am I going to do? I'm going to do the usual. Resolve vertically, resolve horizontally, and then I'm going to take moments, and the obvious point to take a moment is going to be about the point P where the plank is touching the wall, because that's going to get rid of 2 of the forces, and we don't have to worry about whether the fixed mass is to the left or the right of the contact with the block, because of course that would change from a anti-clockwise to a clockwise moment, so we don't have to worry about any of that. So let's do all of these then. So for resolving vertically, I've got F going upwards, I've got an R cos theta going upwards, and I've got an mg going downwards. And for horizontally, I've got an N going off to the right, and I've got an R sine theta going off to the left. So that's those two. And then moments, so I'm going to have an mgx cos theta going clockwise, and then I'm going to have an r times, well, I haven't actually called that anything. I'll call that L for the distance. So let's say where L equals the distance from P to, let's call it Q. So at least I've got that on there. And I need to get X's, D's and thetas in all of this, and possibly something to do with F as well. So I want to get rid of that L, but I can say that L cos theta is equal to D. So that's going to get me a fair way by going through these. So I got that mgx cos theta is equal to r times L, so rd over cos theta. Okay, and I want to get rid of those r's if I can. I mean, I've got d's, I've got x's, I've got thetas. I've got something here for mg, so let's put the mg in, and maybe I can get rid of some r's, or at least shuffle it to somewhere that isn't going to be too much of a problem. So I want to do an mgx cos theta, so that's going to be f plus r cos theta, that's mg. Then multiply that by x. I'll divide through by the cos thetas and do a d cos squared theta over here. So I want to get, so I've nearly got the d sec cubed. So I've got that. So let's divide through then by r. Get rid of that, get rid of that, put that there. And then divide through by cos theta. So get rid of that, leave a 1, make that a cubed, and then put a cos theta there. So just to neaten that up a bit, I've now got f over r cos theta plus 1 times x equals d sec cubed theta. Right, so that works out fine then, doesn't it? Because that's what they're saying then. Therefore, if x is equal to d sec cubed theta, then we've got the contents of this bracket, f over r cos theta plus 1 is equal to 1. So therefore, we got f is equal to 0. So that's exactly what we want. Right, so that was quite a nice little start to the question. Wonder how much of this I'm going to need to reuse on the next bit. Well, I might have to jump back and forward between pages here for a bit. Right, show that if x is greater than d sec cube theta, it's necessary that we've got this. Right, okay, so f is now not going to be 0 then. So we've got if x is greater than d sec cubed theta, then, so what did I have on the previous one? It was f over r cos theta, wasn't it? F over r cos theta plus 1 times x equals d sec cubed theta. So that would mean then that f is going to have to be negative. So means that f is less than 0, because otherwise we're going to end up having something greater than 1 multiplied by x, which is going to make it even bigger, even more larger than d sec cubed theta. So we need to have a negative f on this. So that's going to change some of our equations, isn't it? Where did f? F only appears here. So it's just changing this first equation, this f plus r cos theta one. That's going to have a change of sign to it. So we've now got then that f plus mg, because that's going to, f is now acting downwards, will be equal to r cos theta. And r, I'm trying to remember what r was now. What was r? R is, what's going to be a useful way of doing r? Actually, I can come off of this equation here, this mgx cos squared theta over d. That looks like a good r. So mgx cos squared times another cos, so cos cubed theta over d. Okay, I haven't got any mu's into this yet. I've got that, so I've got that, and I've got f is less than or equal to mu n, and n is equal to r sine theta. That was another one of the, that was resolving horizontally. So I've got here what r is. So all in all then, so I've got the f, it's going to be a long line, this one. F is mg x cos cubed theta over d minus 1. So that's just coming from this. So I've got that. and that has got to be less than or equal to mu times r, which is mgx cos squared theta over d. Yeah, that's it, isn't it? Oh, times sine theta for the r. Right, okay. So hopefully this is, I need to just get mu, this is on the right side of things at the moment to be the subject, and get rid of the mg's, mg. So I've got x cos cubed theta minus d divided by x cos squared theta sine theta is less than or equal to mu. Right, so what have they got? They've got sec cubes in this, so I want to multiply top and bottom by sec cubed. If I do sec cubed theta over sec cubed theta, I'll just turn it around so it looks like what they've got. So that will become an x minus d sec cubed theta. So that's why I've done it, to get, at least it gets the numerator right, and it should make the denominator right, otherwise I've made a mess up. So I've still got an x, and then I'll have a sine theta over cos theta, which is a tan theta. So happy days. Right, so that's done that bit. Give the corresponding inequality if x is less than d sec cubed theta. Right, so that means we've got a positive f. So that means that f is greater than 0. So I'm going to be going back to the old formula then, aren't I? I'll be doing, this is going to have, well, it's going to be the other way round. I'm going to have a minus sign in here. So that would be going the other way. How is that going to change things? I'm going to have, yeah, so it's going to change this thing around, isn't it? Because I'm going to have, yeah, this is going to have a change of sign because I'm going to f plus r cos theta equals mg, and that means I'm going to have the r cos theta the mg minus the r cos theta. So yeah, I'm going to have the f is equal to mg 1 minus x cos cubed theta over d. So I've got a difference to what I've got there. I've just got a flipping sign on that, which means I'm going to have a flipping sign on that. So that will lead to that mu has to be greater than or equal to d sec cubed theta minus x over x tan theta. It's just the same bit of working out. I've just changed the sign around. Okay, so that's good. Part 2 done. Part 3, show that x over d is greater than or equal to sec cubed theta divided by 1 plus mu tan theta. Right, the thing is now I've got these two different possibilities for x, haven't I? We've got the things that are changing, whether I'm going above or below d sec cubed theta. So let's look at each one of those in turn then, see what we're getting for this. So if x is greater than d sec cubed theta, then I've got x over d is greater than sec cubed theta. I need to get a 1 plus mu tan theta in there. But that's just obviously true, though. That's a pretty generous case here. As in, well, if mu is 0, then we're just getting the equality. But otherwise, that denominator is just going upwards, isn't it? So that's got to be greater than or equal to, sec cubed theta has got to be greater than or equal to sec cubed theta over 1 plus mu tan theta, because mu tan theta is greater than or equal to 0. We're not going to get a negative there. So this denominator is going to be greater than or equal to 1. So that's all going to fit. So yeah, I mean, that is it. That bit's done. Also show that, oh no, I've got to do the other thing, haven't I? I've got to do the if x is less than. Actually, can I put the equal sign in here? That'd be nice, wouldn't it? If I could put, yeah, so if I did have x is greater than or equal to d sec theta, that would be greater than or equal to, and that would be greater than or equal to. So that all works through fine. So I don't have to put the equals here. I can just do a straight less than. So if I've got that, let's put a then up there, then what am I doing? I'm then saying that, right, this one looks a bit more involved, really. I think I'm going to have to pull that mu from the previous part of the question. I think. I can't see how I'm going to be able to do this, otherwise it's not as obvious a comparison, is it? If it's going to be less than that, because then we've got two, yeah, the inequalities are going in the wrong direction. I can't do the same trick as I've just done on that previous part. So I'm going to have to say then, so what was it for this one? So mu was greater than or equal to, it was this with a flipped sign. So d sec cubed theta minus x over x tan theta. Okay, so I've got that, which means that I'm going to have, I want to get these x's factorized. So that's going to be x mu tan theta plus 1. I like the look of that. It's got to be greater than or equal to d sec cubed theta. So x over d is greater than or equal to sec cubed theta over, I'll change the order to make it look like what they've got in the answer. So that's come out as well. Right. Show also that if mu is less than cot theta, then we've got that. Okay, so you can see why that inequality is useful here, why it's of interest, because that denominator there, if mu is equal to cot theta, then we're getting 0 on the denominator. So we want to keep that from being 0 or being negative for that matter. So we've got, what am I going to do with this then? So let's go back to blue. Again, we've got the two cases. So if mu is less than cot theta, then I've got then if x over d is greater than, I think, can I go for, I'm going to go for equal. I mean, it sort of worked last time, sec cubed theta. Then I've got, so that was using this one up here. So I can say that mu is greater than x minus d sec cubed theta over x tan theta, which should be greater than or equal to, which means that I've got that d sec cubed theta is going to be greater than or equal to x1 minus mu tan theta. All right, so that's it. That's come out. So that will be that x over d is less than or equal to sec cubed theta over 1 minus mu tan theta. Right, so that came out okay. But now I've got the case of, right, let's hope this will be a quick one. If x over d is less than sec cubed theta, then actually isn't this going to end up being the same as this? The same sort of idea, because then if we've got that being small, I don't know, does it? Yeah, it's got to be, because this thing here, mu is less than cos theta. Is this definitely going to work out? Yeah, if mu is less than cot theta, then that means we've got some number here that, yeah, this is going to work out fine. Then, okay, so mu, or so what I'm getting at is if mu is less than cot theta, then 1 minus mu tan theta is going to be between 0 and 1. Between 0 and 1. Well, it can't be 0, it could be equal to 1. I think is what I'm getting at on here, isn't it? If mu is, oh no, it can't even be equal to 1. Oh no, mu could be 0, yeah, so it could be equal to 1. So I've got that. So that means then that I'm going to have that mu is, x over d is less than sec cubed theta. Yeah, and right, so yeah, I'm doing the same thing. I just don't really know where to write it. So, right, let's do it in, I'll change color again, write it in here. So I'm saying x over d is less than sec cubed theta, which is less than or equal to sec cubed theta over 1 minus mu tan theta, because 1 minus mu tan theta is between 0 and 1. So it's exactly the same argument up as I had for this earlier part. You just see that matching up. They're not very strict, some of these inequalities. You can see that they're, well, that's obviously going to be the case. It's easier in some situations than others. That's always going to be making the right hand side larger if you're dividing by 1 minus mu tan theta. It can only make it bigger or stay the same. It can't make it smaller. So if we're already saying, well, we're definitely meeting that inequality without the denominator, putting a denominator in isn't going to change anything, which is exactly what we had up here for the first part, part 3. Okay, so again, all fine. And then part 4, right, so show that if x is such that the point mass is fixed to the plank somewhere between the edge of the prism and the wall, right, so that means that x is less than L, x is less than L, then what am I saying? And L was equal to d sec theta, wasn't it? Because, yeah, that's right, L cos theta was d, so d sec theta is L, x is less than d sec theta. Then anyway, so that's what we got with that implication of that piece of information. Then we need to show that tan theta is less than mu. Right, so I'm starting off from this point of x is less than d sec theta. So x over d is less than sec theta. And then I've got these things here, these two inequalities. So you're also telling me things about x over d. But the second one doesn't help as much because I'm saying that x over d is smaller than two things. It doesn't help me distinguish which right-hand side here is going to be larger out of it. I'm just saying I've got x is smaller than that and it's smaller than that, but it doesn't tell me what the relationship is between those things. So the first inequality looks more useful because I'm saying that I've got sec cubed theta over 1 plus mu tan theta. That is less than or equal to x over d, and that is less than sec theta. So that looks plausible, doesn't it? I've got sec squared theta is then going to be less than 1 plus mu tan theta. So sec squared minus 1. Let's just make sure I'm not going to mess this up. Sine squared plus cos squared is 1. So I want to have sec squared. So I want to divide by cos squared. Tan squared plus 1 is equal to sec squared. So sec squared minus 1 is tan squared. So tan squared theta is less than mu tan theta. So tan theta is less than mu. Wonderful. So yeah, okay, that came out all right as well. Well, that was quite a nice question. Maybe not the most, I don't know, you end up getting a little bit into the weeds in all the algebra without necessarily thinking in great depth about the implications of all of these things. Although I suppose, I mean, yeah, maybe to be fair on that, did talk about it a little bit at the beginning of how that friction is going to change direction at some point. As we move this fixed mass further away, as we move it further up here, I can't get on the right sheet, here we go. As we move it further up the plank, we get that flip in F, which is what we identify as being, that is the key point, that is the distance x where the friction flips. And then we have to consider situations to do with that position and the coefficient of friction against the wall. So yeah, I suppose it does have a bit more insight into it than maybe I was giving it credit for initially. But yeah, that's a nice question, really. Typical mechanics stuff. So quite pleasing.